Hello everyone. In the previous module, we covered data acquisition using edeX software and hardware. This was the data that we were able to obtain of our motor demonstration. And in this module, we are going to cover how to create a dynamical process model using edeX software now that we have the data. Before we do that, we want to just examine this this graph a little bit or this plot a little bit further in order for us to understand how we're going to model it. Number one, we notice here that when we gave an input to the process initially, there was no response from the process until a certain threshold was met. And likewise over here towards the end, the process suddenly drops to 0. This is a nonlinearity known as a dead zone. And so we're going to go ahead and use that as the first step in our model. Secondly, we're going to use a transfer function. And because we know that motors are typically second order processes, they behave in that manner, we're going to use a second order transfer function. Lastly, we're going to go back here to the plot and notice that when we gave a output or an input to the process of 10, the response peaks over here at 9 point something, let's say around 9.5. So in order to model that, we are going to use another nonlinear block known as a limiter. And we are going to put that upper limit as, let's just say, a little bit higher than what we may think it is. Because in a moment we're going to show how the tuner is going to find the correct value. Likewise with the dead zone, we know that it is less than 2, so we're just going to start with that. Next, we're going to configure our tuner over here. And these are settings that can be varied, but not important for now. More importantly are these settings. So these are the design variables that right now our tuner is going to find according to the optimization restraints, which we actually haven't set yet. Let's go over here to the optimization constraints block. We will use an error criteria. And what we're going to do is we are going to have the error criteria of the response that we get from the data versus what we get from the output of the limiter. Let's go back here and figure out our design variables. So here for the dead zone range, we're only going to do the end only. And so we are going to say 0 and 2. And we're going to have the tuner find the exact number. We've set this up so that if you just leave this blank for a transfer function, it will tune all of the various coefficients. So we're going to go ahead and leave that blank. For the limiter, we are going to once again do the upper limit only, and we're going to say there's a maximum of, say, 9.6. Over here on our performance evaluation, we have our error criteria, and we're going to leave it at 0 so that it finds the minimum. So we're going to just run this simulation first, and we can see here, this is what it looks like beforehand. We can also just plot so you can see this, the input to the process as well. So you can see our original is the red and the black. So the red being the input to the process and the black being the output of the process. And right now the blue is our model. So now we are going to run the tuner, and we're going to see how the tuner is able to find the model. Okay, so we can see that our tuner has already found a decent model. Not perfect, but in order to tune a fuzzy controller, we only need an approximate model anyway. If we want to find a more accurate model, Xiera does have a proprietary method to do fuzzy nonlinear modeling, which can actually make this near perfect, which I will show now. So this is a different data acquisition or data set that we did for the same setup previously. But you can see here in the black is the original or the response of the process, and here in the blue is the model, and you can see that that is as precise a model as you're going to get. Now I can't show the block diagram to show exactly how we did it, because as I mentioned, it is proprietary, but this is just to also give you the idea that it is possible to make some very, very accurate models using fuzzy nonlinear modeling. So back to the original model that we were working on. As we can see here, this is an approximate model. It's not perfect, but it should be good enough, as a fuzzy controller only requires an approximate model. So we're going to go ahead and stop tuning. Or we were already paused, so it wasn't tuning anyway, but we won't further tune. Here we can see on the limiter that it found the upper limit of the limiter. And here you can see that it found the upper limit of the dead zone as well. So with that, we have an accurate enough model. We can go ahead to the next module and create a fuzzy controller.